So this lecture is about binary search trees. What do we mean by binary search trees? So let's take a look at the notion of a binary tree. Now, binary tree is such that it's a structure such that each node can have up to two children nodes or two child nodes. Now, then we add another component called the search part. So the search means that we should be able to search this tree for something. Now, if you recall the binary heap that we talked about, we don't really search through a binary heap because we do know that the only thing we are interested in a binary heap is the root node. So we find the root node, which is always the top node. But in a binary search tree, we must organize elements in a certain way such that we can find them by doing an efficient search. So let's start with an ordering invariant. So let's talk about what the invariant for the order would be. So for example, in this case, we're going to define a binary search tree as such that at any node k, so let's say that if you take a node with a key k, in a binary search tree, all keys in the element to the left subtree, so in this case I'm going to draw the left subtree as a triangle, so all keys in here will be less than k, and all keys in the right subtree are going to be strictly greater than k. Notice that I mentioned that they are strictly less than and strictly greater than left and right subtrees. So this means that binary search trees cannot have duplicates. Now if you have duplicates, you can handle the duplicates in creative ways by the node design. But for now, the binary search trees don't have any duplicates. So this is our invariant. We have to make sure this invariant is going to be true for any binary search tree. So let's look at some of the examples. Let's say that we have the elements 1, 2, 3, and we like to create as many binary search trees as possible. So one possible binary search tree would be that we create 1, 2 is greater than 1, and 3 is greater than 2. So that's one possible binary search tree. So on the other hand, you can go like this. That's another possible binary search tree where all the elements to the left of 3 are less than 3. Or strictly less than 3. Here's another possible binary search tree where you have 1 to the left of 2 and 3 to the right of 2. And here's another possible binary search tree. We can have 1 here, then we can have 3 here, but the 2 would be to the left of 3. This means that 2 is less than 3 and 3 is greater than 1. We can also have a tree that has this shape here, where I would include the largest element here. This would be 3, this would be 1, and this would be 2. So that's also a binary search tree where we satisfy for each node, we satisfy that the left child is less than the node and the right child is greater than the node. So a good exercise would be that try to draw all the binary search trees using the keys 1, 2, 3, 4. And you can draw many of them. Now if you look at all of these binary search trees that we drew, probably this one seems like a nice balanced tree. So we like to have something like this because in case we need to search, we like to keep the height of this tree to a minimum. So trying to get a balanced tree would be a good idea, but it's a hard thing to do as well, and we will talk about that in the AVL tree lectures. So let's talk about designing the tree node and the BST. So in terms of tree node, what we're going to do is we're going to use a tree nodes like this. We're going to define a struct tree, which is defined by 3 things. In other words, when you think about the structure that we are defining, we have a data field, which is an element type, and the element type will be provided by the client. So for now, let's just assume that the client will give me the element type. That can be an integer, that can be a string, or any other type. And then you will have another field called left field, which is really a pointer to one of the structures called tree. And then you have a field called right, where you have another pointer here. So using this nonlinear structure, we should be able to create a tree-like structure. Now this is somewhat similar to the doubly linked list that we discussed, except that in the doubly linked list you have the pointers going left and right, or next and previous. And in that case, it was a linear structure, but in the case of a tree, it's a hierarchical structure. So as you can see, the tree will grow like a hierarchy. So you start from the root of the tree and then you go down by traversing each level. Now when we design the binary search tree node, because you only have one of those things, and some of the key things are the root. Root is a tree node, so you can think of a binary search tree like a data structure where you have a field for the root. So the root is pointed to a tree node, and then you will have the tree nodes in this tree here. Now you can also have another field like a size that will allow us to keep track of the size of the binary search tree, so we do know how many elements are in this binary search tree. Now we don't have a formula yet to find the size of a tree. In other words, how would you find the size of a binary search tree? If you have a list, you know how to find it. You can start from the beginning, you can go to the end, you can just count iteratively until you find the total. But here you have a number of levels, and it doesn't guarantee it's a balanced tree, so we cannot even use the height information to find the number of nodes in the tree. So therefore you'll have to come up with a creative algorithm to count the nodes in a binary search tree. Now, so the next we're going to try to establish the binary search tree invariant. So we're going to have two key functions. One is the order tree. Order tree means that it will take a tree node and make sure that that tree node satisfies the order of the tree. Now, so these are going to be the key functions for our contracts for checking invariants. And then once we have the ordered tree function, we'll be able to use that in a binary search tree code to check whether something is a binary search tree or not. So let's talk about the order tree function that will be used for contract checking. So let's just say that in this case, we will assume that we will think about something like this. We'll say the binary search tree, if you think about a condition like this, that says that for each node, that the left node is less than the root, and the root is less than the right. And the empty tree is a binary search tree. So let's assume that empty tree is a binary search tree. So we ask the question, if for any given tree, for each node, if the left is less than the root and the root is less than the right, would that be a binary search tree? So the question, you have to say either yes or no here. So you can try to give count examples. Like for example, you can say, well, okay, let's take this here. We can have something like 1 here, maybe -1, maybe something bigger than 1 here. So for this one, which seems to be true, because if I take this node, this is less than 1 is less than 2 and 3 is greater than 2. So if I take 1, then you will have 1 is less than -1 is less than 1, but 1.5 is greater than 1. Okay, so I'm going to say for each node that is not a leaf node. Because when it comes to leaf nodes like these, we're not going to worry about children anymore, and because their children are null essentially, so you can always assume that the leaf node, the value of any value is greater than null. And actually you don't want to think about the leaf node, so you can say for each node, the each node that is not a leaf node, then left is less than the root and the root is less than the right. Okay, so if you write a function like that, so you think, okay, well, that is good enough, that's strong enough to satisfy the binary search tree, the invariant, so that you write a piece of code like this. So you make sure that if t is null, we return true, because null tree is a tree node. Otherwise you get the key from the data. So ln key would be a function provided by the client, and then you compare the data field in the left part of the thing. So you take any binary node. So let's just say that k is the one that you're looking at, and then you're looking at the left. So this is going to be the t arrow left. So you look at the data, this is going to be the t arrow right. So you look at the data to make sure that the t arrow left data is less than k. Now keep in mind that the compare function is the standard compare function that we have been using to compare two things. The compare function is also provided by the client. Now then the next line says if k is less than the t right, and if that's true, unless t arrow left is null, that means we don't really worry about the things that are leaf nodes. And otherwise we recursively test this condition. And so the question is this a strong enough function to check invariant? In fact, you can give a counterexample easily to show that this doesn't work. Like for instance, you can have something like this, where you have a tree, where you will have something like, you can have 6 here, you can have 1, you can have 7 here. Now, for all non-leaf nodes that I'm circling here, seem to satisfy that invariant. For each node, that node, like 5 is greater than 3 but less than 6, 3 is greater than 2 but less than 4, 6 is greater than 1 but less than 7, but it doesn't satisfy the BST invariant that says all the elements in the right subtree must be less than 5. But that's not the case, because when you take this element 1, that should not be there. So therefore this is not a strong enough function to check invariant. So this is not strong, so we have to establish a strong invariant. So the way we are going to try to do that is by thinking about a very simple idea here. The idea would be that the elements, if you assume that the elements of the root element can be anywhere between -infinity to infinity. Let's assume that key is an integer for a moment. Then we do know that all the elements in this subtree must be in the interval -infinity to x. X is not included. So it's greater than -infinity but less than x. And all the elements in this subtree are going to be between x and the positive infinity. So we want to create a strong invariant where we not only check the left and the right limits of each of the nodes to make sure that the entire tree is less than the x and the entire right tree is greater than the x. So that's very important for us to check. So for instance, if I give you an example like this, let's say we have 5, we have 3 here, we have 4, we have 2 here, let's say we have 6 and 7. So that is a binary search tree. So what we are saying is that the -5 is between -infinity and infinity. So that's the element -5. If you take the element 3, that should be between -infinity and 5. And then this should be between 5 and positive infinity. It's greater than 5, less than positive infinity. And similarly, if you take this element here, that should be between -infinity and its parent 3. And this element should be between 3 and the positive infinity. And this element should be between 6, its parent, and the infinity. So we can, for each node, we can define a range of values where the node should be between. Now if it's not, then we do know that it's not a BST. So we have to make sure that for each node we're going to be testing this invariant to make sure that the node value is between the proper interval that is defined by this invariant. So we are going to define a function called ordered function. What that will do is to take a lower limit and an upper limit and a tree node and check to make sure that it's between lower and the upper. So once again, we look at the null case. If tree is null, we return true. But if t is not null and the data is null, we return false. It cannot be a tree. Otherwise we get the element key from the tree, so let's call that k. And then we check to make sure that the element key of the lower element, so we start with obviously -infinity and infinity, or null and null, if you can say that. So we compare the element key of the lower, it can be null, to k, and if it's less than 0, so we have to make sure that the element key would give us would deal with the client. We have to tell the client that the lower can be null. We don't have a way to represent -infinity and positive infinity, so we use the null to do that. So and here ln key can be again upper can be null as well. So we have to make sure that the client knows that the ln key must handle the case null. If it's null, then it can be thought of as 0. So we have ln key of lower. We make sure that you compare these things, and then ln key lower to k. And if it violates it, if the lower key has if it's not less than the k, then we should return false. Or in the same case, if the k is not less than the upper, then we should return false. Otherwise, we recursively go to the left subtree, and we recursively go to the right subtree. And in this case, we're going to be changing the lower and the middle, the upper elements in that search, which is somewhat similar to the binary search algorithm we discussed. And we keep recursively looking for the looking to make sure that the tree is an ordered tree. And we will do this implementation in our code. So in terms of client design, what we have to do is client must decide what the key would be and what the element would be. So element can be a pointer. So we like to keep the element as a pointer so that client can be very flexible in designing the nodes that can be used with this library that we are trying to design. So client ln key must also handle the taken element type and provide us with the key. And the compare is the standard compare where you return less than 0 or equal to 0 or greater than 0 based on k1 is less than k2, k1 is equal to k2, or k1 is greater than k2. Now let's talk about designing the library interface. So I'll go over some functions here. So the first function would be bst insert, and the second function would be bst search. We'll talk about some of these ideas in the next slide. So we are going to talk about the idea of search without implementing it. We will do the implementation in the code. So the idea is that given a tree T, so let's call this T, and you're looking for a key K. So the idea would be that if the K is, let's say you're looking for the key 7. So what you would do is you would compare 7 to 8. Since 7 is less than 8, you would go left, compare 7 to 3. Since 7 is greater than 3, you would go right to 6. And 7 is greater than 6, you would go to the right, and now you find the key. So we return the element, we return the value, we found it, that's true. So we return the element once you find it. Now let's just say that we search for a thing that is not in the tree. Let's suppose that we search for something like 12. So if you're searching for 12, what we're going to do is we're going to start here, and then we're going to go to right because 12 is greater than 8. Now we're going to go to right because 12 is greater than 10. Then we go to the left because 12 is less than 14. So now we are at 13. We go to the left again because 12 is less than 13, but we find out that we cannot go no more. So what this means is that the search 12 must return false or null, actually in this case, because we are returning an element always. So if the search returns null, then we know that the element is not found. Now insertion is somewhat similar to search. So let's just say that we like to insert an element into the tree. Let's take something like we are trying to insert 12 into the tree. So if you try to insert 12 into the tree, we compare 12 to 8, go to the right. 12 is greater than 10, go to the right. 12 is less than 14, go to the left. 12 is less than 13, go to the left. Now because as soon as you come to a leaf node, and if there's no pointer going left or right, then that's where you insert at the right place. So 12 will be inserted there. Let's just say that we would like to insert another element. Let's just say that we like to insert 5 into this tree. So the algorithm would be the same. We compare 5 to 8, go left. 5 to 3, go right. 5 to 6, go left. 5 to 4, go right. Now we've come across a null pointer, so we're going to be inserting 5 into that. So as you can see, the insert algorithm always inserts elements as a leaf node. So this can break the balance when you insert to a tree, and we'll talk about in the AVL trees how to fix the tree to make it more balanced. So a deletion process would be something like this. Let's just say that we would like to delete an element like 13. Now if you like to delete element like 13, that's easy. All you have to do is make sure that the 14, this pointer, go to null. So that's an easy thing to do. Suppose we like to delete something like this. Let's just say that we had another element here like a 2. Let's say you would like to delete 1. When you try to delete 1, we run into a problem because 1 already has a child called 2. So where would you put 2? So the idea would be, if you have to delete a node that has one child with the left or right, you would look at the parent, and then you will make the parent's pointer go to that, and then delete this node. So this will maintain the tree invariant, but it doesn't but it still does the deletion in a most efficient way. Now the hardest problem here would be to delete something like 8, an internal node, a node that has 2 children. So the question is going to be, in order to maintain the BST invariant, how would you do this? Now one of the techniques that you can use is that you can go one left and go all the way to the right to find the element that is a leaf node, but that is the closest to the 8. So we can replace 7 and 8. So we can replace 8 with 7, and so in other words we can swap those 2 elements, and now it's a simple problem of deleting a leaf node. Alternatively, I could have gone right and I could have find the largest element, the smallest element in the rightmost tree, or the largest element in the leftmost tree. So the idea of deletion is that when you're trying to delete k, you look at the subtrees of the k, and so you would like to replace the k with either this one, this is the largest element of the left subtree, or this one, this is the smallest, so this is the largest element in the left subtree, or this is the smallest element in the right subtree. So that's the delete process. So we will write the code to do that. Now one other thing I like to do here before we wrap things up is to show you how to do a tree traversal using in-order traversal. In-order traversal is a recursive traversal method that allows us to go through the tree using this criteria. We go to the left subtree first, and then we print out the root, then we do the right subtree. Okay, so if you think about that sort of a recursive traversal method, here's how you want to think about it. We have to process the left subtree first. So when you process the left subtree, you must process recursively its left subtree. So in that case, because that left subtree has only one element, I'm going to print out 1. Now once you print the left subtree, you must process the root node, which is 3. So I'm going to be printing 3. And then you process the right subtree. Within the right subtree, you're going to be going in this order: the left and the root and the right. So that allows us to process this entire left subtree. Once that's done, we should process 8. And then once that's finished, then we look at the right subtree, and then we try to go in that order. We try to process the left subtree. There's no left subtree here, that's null, and therefore we process 10. And then we have to go into the right subtree. There we go left node, and then the right node here. Now as you can see, the sequence that I produce by traversing this is a sorted sequence. So in other words, if you do in-order traversal in a binary search tree, that you will always produce a sorted sequence. That's also another way to check if a binary search tree is satisfy its invariant, and the in-order traversal must produce a sorted order. And this is the conclusion of the binary search tree short video.